Welcome everyone to our presentation. The topic is Corruption Exposes You, Statistical Key Recovery from Compound Logic Locking. I am Arshdeep Kaur, a student of MTech in Computer Science and Engineering from IIT Guwahati, and the other authors of the paper are Dr. Sandeep Saha, Dr. Chandan Karfa and Dr. Devdeep Mukhopadhyay. In introduction, we'll cover these topics. So since the time the idea of fabless semiconductor companies has come into picture, all the manufacturing of the chips have been shifted to offshore third-party foundries, which have led to different hardware security vulnerabilities like IP piracy and cloning, hardware trojans and overbuilding. So idea of logic locking came into picture. So in logic locking, we introduce additional gates called key gates, which are controlled by key inputs called secret key. The secret key will be stored in a tamper-proof memory and loaded at the time of activation of chip. And this is the basic idea. So this is an example of logic locking. The black part of the circuit is the original circuit and it has been locked using some key gates which are shown in the red part, and it will be controlled by the secret key K1, K2, K3 whose correct value would be 1, 0 and 1, and if wrong keys are applied the output will be erroneous. So for random logic locking, we insert the key gates randomly and so that there is minimal interaction. And for stripped functionality logic locking, we strip some functionality from the circuit which induces a built-in error and which is cancelled by a restore unit only by application of the secret key. RLL has high output corruptibility but it is vulnerable to attacks, whereas SFLL has highly resilient nature towards attacks, even SAT attack, but is very less output corruptibility. Now to overcome these limitations, two logic locking schemes can be combined, and the schemes we will use will be RLL and SFLL. RLL will provide high output corruptibility and SFLL will provide resilience against the attacks. Now, for motivation, we define a circuit called C original. This is C encoded circuit obtained from C original circuit using compound logic locking. There is no standard procedure for compound logic locking. So first we lock the C original circuit using RLL and these are the correct keys, and then we lock it using SFLL and these are the correct keys. Let us consider four wrong keys to the C encoded circuit. Wrong key 1 says all RLL keys are wrongly fixed. Wrong key 2 says some of them are wrongly fixed. Wrong key 3 says some SFLL keys are wrongly fixed. And wrong key 4 says some RLL as well as some SFLL keys are wrongly fixed. And those are shown in the red color. Now this is the output distribution for different keys. From here, we note that for wrong key 1, 4 out of 8 outputs got corrupted. For wrong key 2, all the outputs got corrupted. For wrong key 3, only one output got corrupted. And for wrong key 4, 4 outputs got corrupted. So from this we observe that output corruptibility is high in case of wrong RLL keys, whereas it is observed to be very less in case of wrong SFLL keys. So we can say that correct output and the wrong RLL key output are observed to be statistically distinguishable, and the same cannot be said about wrong SFLL key output. So our motive here is to utilize this statistically distinguishable characteristic and come up with a statistical approach to recover RLL keys to the circuit, and for doing the same we will use the WelchT test. For proposed approach we will discuss these topics. WelchT test is an unequal variance test to sample test and it is a modification of student's t-test. So the test is to determine if two sample means are significantly different. So we'll consider two independent samples A and B and then calculate the t-value with respect to it. By calculating the mean variance in sample space, we can calculate the t-value like this. If it is low, the difference in samples tend to be small, and if it is high, the difference in samples tend to be more. Consider a circuit C with these many inputs, keys and outputs, and now apply random input vector I and random key vector K to the circuit C to obtain the output vector O. So for generating two samples of data, let us consider a wrong key wk. It will be random, and then a random input vector set of size m im. Now apply this input set to Oracle and obtain OCK. Then apply the same input set to the circuit with the wrong key wk and obtain OWK, and then perform WelchT test on these two samples output bitwise. Here, the left one is the distribution for OCK and the right one is distribution for OWK. Each column in this data represents the output distribution with m inputs for one output bit. So the first column is for the first output bit, and the WelchT test will be performed between these two sets of samples, and then for output bit 2 and so on till NO output bit, and so there will be total number of NO WelchT test performed. There is this work TVLA where they have shown that the threshold of 4.5 standard deviation can be set as critical value in case of WelchT test, and we will use the same. And if a particular t value exceeds the band of plus minus 4.5, it is considered as high t value. And if for that particular output bit there is a high t value, we can say key WK is significantly affecting output bit O. Now, the attack model, since it is an Oracle based attack, what we need is a gate level design of the logged IC and the Oracle. Certain thresholds are required because our data is random and we need to conclude to a certain point. So random key set size and random input set size are two thresholds which in our work are considered as equal and set to a random set size of tau. And now we need a probability threshold to filter the key bits showing highly similar patterns. So as an input to the algorithm, we need the oracle. We need the random set size, probability threshold for filtering the keys, the sat found keys, which I'll explain later, and also to decide high corruptibility output nets, we can use output probability threshold. So the overview of our approach, first of all in phase 1 we generate the initial random key set and input set, and then this also comes in phase 1 that we perform one set of WelchT test. Then in phase 2 we find highly affected output bits using the output probability threshold, and in phase 3 we find the keys using highly affected output bits and probability threshold, and I will explain all these later in detail. This would be one iteration. Now if at least one new key is found, we repeat the process from phase 1 to phase 3. If no new key is found, we need to double the threshold tau. Now if no new key is found in two consecutive iterations, we need to terminate the process, otherwise continue with the double threshold from phase 1 to phase 3. The purpose of the SAT keys is to rule out the hard work that has already been done and complement the SAT attack to find more keys on top of it. And for our work, we will use this SAT based partial attack on compound logic locking work as the reference is given in the bottom. And this part is optional. So what is one set of WelchT test? Basically, we generate the random key set and input set on the basis of value of tau, and now fix previously found key bits in that random key set. We can also fix the SAT keys if required. Now for the first sample of WelchT test, we need to generate the output from Oracle with this particular input set, and it will be called OCK. And now for each key WK in K random, we need to generate the output from the circuit, which will be called OWK. Now we perform WelchT test on OCK and OWK output bitwise as it was explained earlier to obtain a t value set T. And we should note that we will perform a total of NO number of WelchT tests for this particular wrong key. And now, after the tests are over, for each wrong key in K random, we combine all such T value sets obtained and form a set Tk whose size will be tau cross NO. And for analysis, we will use the threshold plus minus 4.5. To find the highly affected output bits, we need to traverse for each output bit O in the circuit, and for each T in Tk we stored for that O, we need to see that the T value is high for that particular output bit or not, and if that is yes, then key Wk corresponding to T is significantly affecting output bit O. So we say that T is a high T value set for that particular output bit O. Now, if the number of such high t-value sets is greater than the output probability threshold, then O is high, and all such high O are stored in a list, and also the keys respective to them are stored in another list. So finding keys using highly affected output bits and probability threshold, what we need to do is traverse all the high output bits which we just discovered, and now find the key bits in the cone of influence of that particular output bit. For each key in the cone of influence, we need to check what is its value in the keys corresponding to high output bit O. Now if the probability of those keys being 1 is greater than equal to the probability threshold, then we need to flip it. K will become 0, and if the probability of K being 0 is greater than equal to probability threshold, then also we flip it. So K equal to 1. So add the key if it's not already present in the found list, otherwise ignore it. Now, what is the significance of flip? Our data is random, we know that, and so if the key bit we are investigating is 0 most of the times, and we have a high t value corresponding to that, that means maybe the high t value is because of it being 0. So that is why we flip it to 1, so that it will bring the t value within the range. Same follows if the key bit is most of the times 1. And so what does probability threshold signifies? That a key bit is highly affecting an output bit or not. So now the following slides have the algorithms and the explanation which I have already explained. So verification is needed to minimize the error rate. So in each iteration for each new found key bit k, what we do is we take two random key vectors k1 and k2, and in k1 we fix the value of k as it is, and in k2 we toggle it, and then we perform two set of WelchT test, one with k1 and oracle output and the other with k2 and oracle output. Idea about verification is that if by keeping the key we have found as it is, then the t value should be within the range, and if by toggling it the t value becomes out of range, that means that that particular key bit is making significant difference, and we can see by toggling it, and that is why we propose a verification method. So robustness of logic locking, how do we explain this? So it is directly determined by the keys recovered in our approach, especially in verification process. Since most of the keys found are RLL keys, that is the point where circuit is leaking information. And we can also say, since we have found the mostly high affected output bits, we can say that those bits and the cone of influence are the where the circuit is weak, and we can call such points weak points. And if all the major keys lies in those weak points, we can say that the circuit is not robust enough. Also, we can add extra security on the. Now for results section we will consider. So we will perform four types of experiments. M1 is the statistical approach without verification process. M2 is the same as M1, but we fix the SAT keys found by this particular work, SAT based partial attack on compound logic locking. Then M1 plus verification, and then M2 plus verification. For benchmark description, we have used three benchmarks from Seesaw 2019 Logic Locking Contest, small, medium and large, and these are the details. And the same benchmarks were used in SAT based partial attack, and they were able to retrieve 20 keys from small, 50 keys from medium and 45 keys from large. To see the overall result, we first will investigate the method M1, where SAT keys are not fixed. For small, total of 16 keys are found, and out of them 2 were wrong. The new keys can be understood as SAT found keys minus total keys. So 6 new keys are found. And with verification, total of 9 keys are found and none of them is wrong, and 5 are the new keys. Now the number of keys can be seen for medium and large also. And for method M2, where we fix the SAT keys, for small we can see 13 total keys were found, out of them 4 were wrong, and the new keys were 9, that is 9 keys are found on top of SAT keys. And for with verification we can see 5 keys are found on top of SAT keys, and we can see the number of keys for medium as well as large. For this we can observe that the wrong keys has been totally eliminated with verification process. Here in this trend analysis, we can see that the number of keys recovered are shown and the one in the bracket are the wrong keys. For probability threshold 1, we can see there are certain wrong keys for lower probability thresholds, but as we move on to higher probability thresholds like 400 and 800, the error rate is totally finished. Now for probability threshold 0.9, this is the data, and for probability threshold 0.8, this is the data. Here we can see that as we move on away from probability threshold as 1, the error rate is still there. So let's use probability threshold 1 for our work. Now here we can see in M1 plus verification that a higher number of the tau like 800 and 1600 give zero error rate, and the number of keys do not vary with the if we decrease the probability threshold that much. So we can say that probability threshold is a secondary threshold we can use. The main one is tau and it should not be as low as 50. Minimum we should keep it to 100, and then we can increase it to 800 to 1600 as we have done in our work. So we have varied tau from 50 to 1600 and probability threshold from 1 to 0.6, and I have explained how the varying of these parameters affect the number of keys and wrong keys, and it is totally dependent on the user what to choose. Coming on to conclusions, so this is the first time it has been shown practically that a statistical method has been proved to partially recover keys from a compound logic locked circuit. Compound logic locking is hard to break, and so we all the keys we have found in our verification process is RLL keys, and verification process removed all the SFLL keys because of its SAT resilient nature. Now we were able to find many more keys on top of the SAT based partial attack also. So we can say this approach is not a rivalry to SAT attack, but it can be used in complement to SAT attack. The verification algorithm has removed the error rate totally, and verification has also reduced the number of keys to certain extent, but that is okay. And now robustness of logic locking can be determined directly by the number of keys recovered in verification process. Also we were able to find some weak points of the circuit. For future scope, we can try a brute force exhaustive verification method or a more targeted approach by taking keys in orderly manner. But the main point is that we can improve the security of the circuit by adding extra security on the weak points. That would be all. Thank you. If you have any questions, you can mail us at over here.